Here we go again. The title of this talk is Cannot Measure One-Way Light Speed. I'm going to be referring to this video called Why the Speed of Light Can't Be Measured. By light speed, I mean light speed in vacuum, free from the influences of such things as gravitational fields and other fields. The thesis is that two-way light speed can be measured, but one-way light speed can't be measured. What is meant by these two different types of light speed will be explained anon. So this is the introduction to the video I referred to about no one can measure one-way light speed.
I know what you're thinking. Clickbait! No one has measured the speed of light? That's ridiculous. The speed of light is exactly 299,792,458 meters per second. We are so sure of it that since 1983 we've actually used the speed of light to define how long a meter is. It's just the distance light travels in a vacuum in 1/299,792,458 of a second. That definition ensures that the speed of light is exactly this number, no decimals. But hear me out. In this video, I will prove to you that light may never actually travel at this speed. And I can say that because no one has actually measured it. We can't measure the speed of light the same way we measure the speed of anything else.
So what he's referring to is no one can measure the one-way light speed. I'm cutting out all the laughing that's going on and just presenting the basics. Next, consider how to measure the speed of a baseball.
This is a video about measuring the speed of stuff. Okay. Tell me about how you measured the speed of the baseball fired out of your cannon.
Well, to get the speed of the baseball, you need to know two things. You need to know the distance between 2 points, and you need to know the time that it takes the baseball to travel between those points. So basically, we took distance divided by time, and that's the speed of the baseball. And in our case, we were shooting with a high-speed camera, so you basically just count the frames, and then your clock is internal. Oh, you're going relativity. You're going to do something weird, aren't you?
Yes, going to do something weird. So the question arises, could you measure light speed in the same way as you measure the speed of a baseball?
Imagine you have a laser that can fire a beam through a perfect vacuum for 1 kilometer. Start a timer the instant you fire the laser beam, and then exactly when it hits the end, stop the clock. Except, how do you know when light reaches 1 kilometer if you and the clock are at the starting point? Okay, so you need 2 clocks, one at the laser and one at the end, which stops automatically when it detects the laser light. But now, how do you make sure your 2 clocks are synchronized? Well, you could connect them via a wire and send a pulse from one to the other, but that pulse will travel at the speed of light, so it will arrive with a time delay. You might think you can just subtract that time delay, but it is equal to the time it takes for light to travel 1 kilometer. That's what we don't know and are trying to measure. Okay, new plan. Start with the clocks together and sync them up first, and then send one of the clocks down to the end. Now, what could possibly go wrong? Well, I'll tell you. The clock at the finish line was moving with respect to the one at the start, and special relativity tells us moving clocks tick slow relative to stationary observers. So by the time the clock reaches 1 kilometer, it will no longer be in sync with the clock at the start. Can I?
Okay. So what he's been doing is trying to measure light speed one way with two clocks, and the only solution seems to be to deal with one clock and have the light emitted from where the clock is and then reflected back to the clock, so you're measuring the time it takes for a round trip, i.e. measuring the two-way light speed. So he's going to explain that now, about measuring the two-way light speed with one clock.
I tell you the only solution to this problem? Ditch the second clock. Put a mirror at the end to reflect the light back, and use a single clock at the start to time the full 2-kilometer round trip.
Wasn't this actually done before? He was on a mountain, and there's a wagon wheel with a lantern, and there's something like a mirror on the other side of the mountain. I've always wanted to do this.
So, that sounds a little like how the speed of light was first experimentally measured by Hippolyte Fizeau in 1849. He shone a beam of light between the teeth of a rapidly spinning gear to a mirror up on a hill 8 kilometers away. And then, by increasing the speed of the gear, he reached a point where the reflected light passed through the next gap on the gear, and so it was observed. So he measured the speed of light to be 313,000 kilometers per second, which is within 5% of the presently accepted value.
Okay. So they're measuring two-way light speed and not one-way light speed. So he now continues with this.
What has been measured is the round trip or two-way speed of light, but no one has measured the one-way speed of light.
So now that you haven't measured or can't measure the one-way light speed, what if light speed is different in different directions?
It's like, what if the speed of light in this direction is different from the speed of light in this direction?
And now he admits to not thinking of this before, i.e. when he was first being taught relativity.
This is hardcore. I've never thought about this.
I didn't think about this before either. I always assumed that when we said the speed of light is c, we meant the one-way speed of light. There's no way to define the one-way speed of light. So the only thing we can really define is the two-way speed of light. Just look at the way Einstein defined c. It's for the round trip from A to B and back. I don't know if you saw in your physics classes, but whenever there was a light clock, it would always bounce the light up and then back. You would never see a light clock just bounce light one way. And this is why. The only thing we can be certain is constant for all inertial observers is the two-way speed of light. For over 100 years, scientists have tried to find a way around this, to measure the one-way speed of light by itself.
So, given all that, he now continues.
Think about communicating with an astronaut stranded on Mars. Let's call him Mark. We send out a signal and get a response 20 minutes later. So we imagine our signal takes 10 minutes to get there, and the reply takes 10 minutes to come back. But it's possible that our message took all 20 minutes to get there, and the reply came back instantaneously. There's no way we could tell the difference between these two scenarios. But why would the speed of light be different? Well, it's possible that there is some preferred direction through space-time. I mean, our universe has a lot of symmetries, but there is also some asymmetry. For example, why is there so much matter relative to antimatter? And physicists have worked out internally consistent theories of physics in which the speed of light is different forwards and in reverse. The speed of light could vary by just a few percent, up to, at the extreme, going c/2 in one direction and infinitely fast in the other direction.
Okay, so you get all that. It shows how little we can actually know in physics. And so I think he has a little laugh about that and continues.
Now, you might think it is just simpler that light should travel at the same speed in all directions, but the truth is that is a convention rather than an experimentally verified fact. Einstein himself pointed this out in his famous 1905 paper on the electrodynamics of moving bodies. He spends the first couple of pages on the problem of synchronizing clocks at different locations, A and B. And he says, there is no way that we can meaningfully compare the times they measure unless we establish by definition that the time required by light to travel from A to B equals the time it requires to travel from B to A. He's essentially defining that the speed of light in opposite directions is the same. And he puts, by definition, in italics to remind us that this is only a convention. It's known as the Einstein synchronization convention.
So he refers to a translation of Einstein's paper from German into English at this website here, and what I want to point out now is that is a mistranslation. I have argued with various relativists, and one of the things I pointed out is that Einstein's papers are full of mistakes, but they keep getting reprinted without any corrections to the reprinting. The excuse given by these relativists is to think that is okay, to leave the mistakes in every reprinting because it is being treated as historical documents. I mean, you could naively think, well, if there was a mistake in the original printing, they would correct it in the next reprinting, but they don't. So what it ends up with, he is now quoting from a paper with mistakes in it. It's a reprinting of a paper with mistakes in it. So what he is quoting is wrong. So we go into that now. Now, what I'm referring to is an article referred to as a mistranslation of a passage in Einstein's original paper on relativity. And this is the American Journal of Physics, published in 1963. So if you think in terms they would correct a mistake in a reprinting of a paper that's got a mistake in it, well, no, they don't do that. They just leave the mistake in it. And it was pointed out in 1963 that this paper had a mistake in it. But they just ignore it on reprinting, and it leaves people to just then look at a paper which got loads full of mistakes. Now this is the article. It says, students of the special theory of relativity who have read Einstein's fundamental paper, which translates to English as on the electrodynamics, may appreciate our pointing out the following passage in which an unnecessary elaboration of the text on the part of the translators has somehow altered its exact meaning. we quote below the original passage and then the translation, placing brackets around the questionable part of the latter. So it then quotes the German, and the translation is, but it is not possible without further assumption to compare in respect of time an event at A with an event at B. We have so far defined only an A time and a B time. We have not defined a common time for A and B. Now in the square brackets, this is where the mistake is, for the latter cannot be defined at all unless we establish by definition, and that is a mistake. That the time required by light to travel from A to B equals the time it requires to travel from B to A. The article goes on. A faithful translation of the last sentence of the passage in question would read simply, the latter time can now be defined in establishing by definition at the time, etc. So the thing is, the word is now. And this is what Einstein said in 1921. The theory of relativity is often criticised for giving, without justification, a central theoretical role to the propagation of light, in that it founds the concept of time upon the law of propagation of light. The situation, however, is somewhat as follows. In order to give physical significance to this concept of time, processes of some kind are required which enable relations to be established between different places. It is immaterial what kind, and so forth. I'll leave you to read the rest of it. So that is where the mistranslation is. So it is convention to have one-way light speed as c, the normal symbol for it, and it's not often taught that way to physics students, so it is moving goalposts. As per Wikipedia, moving goalposts means derived from goal-based sport. That means to change the criterion or goal of a process or competition while it is still in progress in such a way that the new goal offers one side an advantage over an advantage or disadvantage. So in the case of Einstein's theory of relativity, they keep changing, moving the goalposts. What is presented as special relativity has its goalpost moved. Suddenly we are now told about one-way and two-way light speed and convention, when normally that's not taught. That is goalposts being moved. Also, if you look at the 1905 paper by Einstein, he says nothing about such things as one-way light speed and two-way light speed. Those are terms he did not have in 1905 and were invented later. So it's more moving goalposts on introduction of those terms. Without those terms, can look at his paper and not realise there are different types of light speeds being referred to, and that can lead to further misunderstanding. In my view, the mistranslated paper is referring to a different theory than the correctly translated paper. I have argued this in several of my talks. The correctly translated paper means that it's optional to go with the proposed mathematics, and if it's optional, then can stay with the existing mathematics which is familiar to Newtonian physics, i.e. we have here is no change from Newtonian physics. It is just the adoption of convention to be added as optional to Newtonian physics, along with a lot of other things. You're just adding extra things to Newtonian physics. Normally you wouldn't use this convention, but it doesn't matter to Newtonian physics, you can add it if you wanted to. He continues his talk.
So the idea that the speed of light is the same in opposite directions, as Einstein would later write, is neither a supposition nor a hypothesis about the physical nature of light, but a stipulation that I can make of my own free will to arrive at a definition of simultaneity. That sounds a lot more subjective than how I think most people would imagine the speed of light is defined.
Dude.
So he is admitting it is subjective. This convention is subjective. And if it is subjective, then we can stick with Newtonian physics. So he continues.
This is hardcore. I've never thought about this.
I didn't think about this before either. I always assumed that when we said the speed of light is c, we meant the one-way speed of light. There's no way to define the one-way speed of light. So the only thing we can really define is the two-way speed of light. Just look at the way Einstein defines c. It's for the round trip from A to B and back. I don't know if you saw in your physics classes, but whenever there was a light clock, it would always bounce the light up and then back. You would never see a light clock just bounce light one way. And this is why. The only thing we can be certain is constant for all inertial observers is the two-way speed of light. For over 100 years, scientists have tried to find a way around this, to measure the one-way speed of light by itself.
What he refers to is physicists that are aware of the problem. If you're a physics student, you are probably not told about this problem. He is admitting that he did not originally know all of this about one-way light speed and two-way light speed, and he did not know that it was a convention to have a one-way light speed as c. I take that to mean he hadn't been taught relativity very well. He'd been taught wrong. If you're taught wrong, it is moving the goalpost to suddenly decide that what has been taught to believe is not what the theory really is. Now, relativity is full of these sort of revisionisms. People who get taught things and then later they have to, if they're faced with certain other problems, they have to realise that what they've been taught has not been actually correct, and they have to then take a revisionism. So he continues.
What if you center a synchronizing device between your two clocks and send out simultaneous pulses? Well, if the speed of light is the same in both directions, this perfectly synchronizes your clocks. But if the speed of light is different in each direction, one of the clocks will be ahead of the other, and it will be ahead by just the right amount, so that when you measure the speed of light, you'll find the value to be c, even though that was not the speed the light was traveling. This is the same reason GPS synchronized clocks won't work. The whole GPS system is based on the assumption that the speed of light is the same in all directions. If the speed of light is different in different directions, the light pulses from satellites will travel at different speeds, so the clocks won't be properly synced. By that I mean they will always measure c for the one-way speed of light, whether it is or isn't. How about starting with synchronized clocks in the middle and moving them apart with equal and opposite speeds? That way the time dilation for each clock will be the same and they'll still be synchronized when they reach the endpoints. But again, this only works if the speed of light in each direction is the same. If the speed of light depends on direction, then so does time dilation. You might think you could move the clocks really, really slowly so that time dilation is negligible. But if the speed of light is different in different directions, you can't just use the standard formula to calculate what that time dilation would be. I mean, it could be a lot worse than you think.
So the reality is we're stuck. We need synchronized clocks to measure the one-way speed of light, but we need to know the one-way speed of light in order to synchronize our clocks. Now this might...
So that's all circular thinking. In order to synchronize your clocks, it's circular with the idea of one-way light speed. I'll finish showing his video from this point on because I start disagreeing too much with what he next wants to say. At the end, he finally talks about all this giving new insights into physics, but as far as I'm concerned, it's all just still Newtonian physics with strange things added to it about such things as convention, with people being taught relativity in a bad way, so they get misunderstandings about what Einstein's relativity really is. So that's the end of the talk. Thank you. Bye.